There are many needs for the rapidly expanding world of neural net-based artificial intelligence. The most obvious one is the need for training data, and particularly for high-quality labeled data. This is being generated and tracked by companies all over the world. It used to be that companies provided free services in order to be able to sell ads to viewers, but now many of them seem to be providing free services in order to gather data from users that they then sell. But in this lecture, I'm mainly going to be talking about the physical needs associated with machine learning. In the 1880s, Thomas Edison, George Westinghouse, and Nikola Tesla competed to start selling electricity to customers. For the next 120 years or so, electricity generation in the United States kept rising. Interestingly, a few years after 2000, electricity generation has leveled off in the United States. There's been a massive rise in natural gas and renewable energy, but this has mostly been replacing the phase out of coal. It does seem likely that this is going to have to change, though, as the electrification of automobiles and household and industrial processes occurs, and especially as the electricity needs of data centers start to rise. It's obvious that a lot of electricity is required to power the computers that do the calculations needed to train AI and to operate it. But it turns out a lot of energy is also needed to keep the computers cool. All the electricity they're using generates heat, and then they need to pump out that heat. This has been getting somewhat more efficient. Back in 2007, it was nearly 2.5 times as much electricity needed to run a data center as the amount that the computers themselves were using. These days, it's more like 1.5 times, but it's still a significant fraction. There's electricity needed for the computing and electricity needed for the cooling. And one interesting thing to note is this is where data centers have been located around the world in recent years. This is as of 2023. Note that the way they measure how much data center capacity there is in each location is by the amount of electricity used, rather than by the square footage of the data centers or by the number of computers. Electricity turns out to be the most obvious metric for these things. The biggest clusters of data centers are just outside Washington, D.C., and a secondary one outside Beijing. And there's, of course, other clusters in cities that have major telecommunications infrastructure or major computing companies like Silicon Valley. Uh, but there are a few notable places on this list that have a lot more data centers than you would expect from their importance to the rest of the economy. And these include places like Portland, Oregon, Dallas, Texas, and Reykjavik in Iceland, all of which have a feature in common, which is excellent access to cheap and clean electricity. In Portland, there's a large amount of hydroelectricity. In Dallas, there's a huge amount of solar and wind power coming online, so much that they're having trouble connecting it even to the electricity grid, and so data centers are just scooping it up. And in Reykjavik, they have a lot of geothermal electricity. In Portland and Reykjavik, they also have lots of cold water to chill the data centers. Now, it remains to be seen whether either bottlenecks in new availability of electricity or the shift to AI from other applications of data centers might change where data centers are located in upcoming years from this map in 2023. However, the biggest distinctive new demand for neural net-based AI is computational power. So here's the history of how much computational power was used to train various AI systems from the past decade or so. Notice that this is on a logarithmic scale. Each line here is 100 times as much computation power as the line below. And so GPT-4, released just over a year ago, took about 100 times as much computation to train as GPT-3 did, trained in 2020. And GPT-3 itself took nearly 1 million times as much computation as AlexNet way back in 2012. One thing to keep in mind, this is the amount of computation used to train the model. Recall that training a neural net requires passing it over every single item in the training data, doing a tweak to the weights and biases every time you do that, and then doing this thousands of times to get a good fit on all the data. Actually using the neural net, just making a single call to it to identify a single image or generate a single word in a large language model, is going to use millions or billions or even trillions of times less computation and energy than training it. Still, as these models have grown exponentially, it may well be that a single call to some of the more recent models uses more energy and computational power than the entire training of some of those early neural nets. Now, one thing to notice, this exponential increase in the amount of computation power used and electricity used is partly accounted for by Moore's law, which is the observation made by Gordon Moore, the founder of Intel, one of the most important early semiconductor companies. He noted that the number of transistors on a chip was doubling every year or two. And in fact, when we follow that pattern, all the way from 1970 to 2020, it looks like that rate of doubling has basically continued uh, over 5 decades. Now, one thing to note, this increase in the amount of computational power available by chips only goes up by a factor of 10 or 20 every decade, as opposed to the amount of computational power used by neural nets has gone up by over a factor of well over 1 million in a decade. But one thing to remember is that Moore's law, as transformative as it has been in a continuous way over these past 5 decades, is still only about one particular form of computational power, the transistor. The transistor has been the dominant form of computation for several decades, but there's no reason to think that it will always continue being the most important one. Throughout this entire period, transistors have been made out of silicon, and that specific element has been so essential to them that it gave its name to the entire industry. But there may well be a change in the near future. We're very close to the point where each transistor is somehow just a single atom. There's going to have to be changes. And if we look back in the past, there were changes before. Back in 1950, when Alan Turing was writing Computing Machinery and Intelligence, there had already been several major changes in how computers were built since the machines that he worked on during World War II. But even in 1950, after these changes, the logic on the computers was being done with vacuum tubes, not silicon. And the memory storage in these computers was literally sending an acoustic echo through a tube of mercury. By 1980, 30 years later, when the first expert systems were being deployed so that AI was beginning to have impact in hospitals and corporations, there had been several changes in how computers worked. Liquid mercury had been replaced by magnetized tape and little disks, and long-term storage had phased from punch cards to these same magnetic disks. Computation itself had moved from vacuum tubes to the silicon transistor, and then from the individual transistor to these microchips that had thousands of transistors on them. 30 years later, when AlexNet was the first neural net to win major image classification contests, and neural nets were starting to really show their value, there'd been even more changes. Magnetic disks had been replaced first with optical disks like CD-ROMs and DVDs, and then again by solid-state memory. Microchips were still the main computational source, but they'd gotten 1,000 times more powerful and smaller, and there was a major new development in this time called the GPU. The GPU, or Graphics Processing Unit, was originally developed, as the name suggests, for computer graphics. Both computer games and movies involved lots of simulations of three-dimensional objects, which then had to be projected onto the screen in a way that a viewer could interpret. And this required a bunch of computational power, but importantly, it's a very simple type of computation that just has to be done at every single pixel independently. All they needed to do was do certain matrix multiplication at every single pixel in the visual field, as opposed to the central processing units of other computers had to be able to do any sort of computation whatsoever, and they had to often wait until the previous computation was done before they could do the next one. So rather than trying to speed up these general purpose chips, it turned out to be more useful for computer graphics to create these special purpose GPUs that could do millions and millions of these calculations in parallel. For the first few decades of GPUs, They were mainly just used for computer graphics, as their name suggests. But one of the big breakthroughs in neural nets that AlexNet in particular showed was that graphical computations were not the only things that could be done by the same sort of parallel matrix multiplication. It turns out that the computations needed to train neural nets are this same sort of thing. And one of the things that a symbolic reasoning AI had to do is that they have to do all of their general steps in sequence, while a neural net, even though it might need to train billions of neurons, it can do this in parallel. Now, one of the interesting things is that at present, in 2024, these GPUs are suddenly extremely essential to current generations of neural nets, and neural nets are central to AI. But these GPUs are mostly made by a single company, NVIDIA. At this point, NVIDIA chips are about 80% of all GPUs, and AMD is the source of most of the rest. Intel, which used to dominate transistors for decades, is now a distant third. It still leads in certain applications for desktop computers, but the kind of data centers that are needed for AI are by far relying on NVIDIA. Interestingly, in early 2024, NVIDIA passed Google and Amazon and even Saudi Aramco, the national oil company of Saudi Arabia, to become the third most valuable corporation in the world, behind only Microsoft and Apple. Interestingly, as recently as the end of 2021, NVIDIA wasn't even in the top 10 most valuable corporations in the world. We'll see whether this extremely high importance for one corporation lasts or goes away as quickly as it came. One other interesting thing is that while I'm talking about NVIDIA's dominance of GPU sales, they don't actually manufacture the chips, and neither does AMD. They both contract with these foundries, the Taiwan Semiconductor Manufacturing Corporation for the most part, and also Samsung and various other companies that manufacture other chips. There's a possibility that Intel might move into this business and give up on their own chip design. TSMC is, in fact, it's now one of the top 10 largest corporations in the world. And other than Saudi Aramco, it's the only one that's headquartered outside the United States. And for the record, Samsung itself is the 23rd most valuable corporation in the world as of today. And it's out of all Asian corporations, only TSMC, the Chinese corporation Tencent, and Saudi Aramco are higher in value. Though Samsung, of course, probably most of its value comes from product lines other than microchips. Now, one thing that's worth noting, it's not just TSMC and Samsung that have the high market share in the manufacture of these chips. As I said, these chips are getting very close to the atomic level in size, and they depend on very specialized high-frequency light sources to do lithography for these chips. And in fact, there's only a few companies in the world that make the kind of lithography equipment that do this. And in fact, nearly 80% of the world's supply of this lithography equipment comes from a single corporation, ASML, based in the Netherlands. And out of the rest, the vast majority of that comes from two Japanese corporations, Canon and Nikon. ASML, which is a company that you may not have heard of if you're not paying attention to semiconductor manufacture and the equipment that goes into it, is itself now one of the 30 most valuable corporations in the world. And in fact, in the past few days, it's been back and forth with the second largest corporation in Europe, behind Novo Nordisk, the manufacturer of the weight loss drug Ozempic. Now, interesting, note what countries these companies are based in. They're based in United States, South Korea, Taiwan, Japan, and Netherlands in the European Union. None of these corporations are based in China, and these ones make up the vast majority of the manufacturing, designing, and input supplies for these chips. None of them are based in China, though there are a few competitors in some of these categories with a few percent market share that are based in China. And in 2022, all of the countries that these companies are based in agreed to joint export controls banning the sale of their highest end products to entities based in China. These export controls were then expanded last year in 2023 Though as I record this video in early August 2024, it sounds like there's some disagreement among these countries about the extent to which this embargo of China should continue or whether it might be weakened in some way. It remains to be seen whether the impact of these export controls on the future of the development of artificial intelligence is as significant as the 1973 Arab oil embargo, leading China to fall behind the rest of the world in advanced AI, or whether the Chinese companies that have a few percent market share in these categories will start to expand.